So characterization is a last and extremely complicated step of exoplanetary analysis. I will speak about only transiting exoplanets. So after detection of a candidate, we have to validate, which means in my terminology that we prove that it is not a bland and its mass is in the planetary range. Then we confirm the planet, which means in my terminology that that the mass of this candidate is we learn the mass of this candidate, and then we characterize it. And characterization means that we can measure, and we will measure, a lot of different planetary parameters. The most important ones are the planetary mass, radius, the orbital elements, and we can measure many other things. I will concentrate only on the planetary radius because this is one of the most important parameters, and many other determinable planet parameters depends on the planetary radius and on the precision of the planetary radius. So yesterday we had talks how to characterize the masses of planets, and we had a talk about the non-spherical stars, how it affects the characterization of the planets, and there will be another talk this morning by Ray Javadara about the phase curves of the exoplanets. So let's turn to the motivation. So why do we need precise planetary radii? This is a mass radius diagram of exoplanets, and you can see that we have considerably big error bars, both in mass and radius. And it was quite clear before the CoRoT and Kepler era that we have to know the masses down to 10% precision and the radii down to 5% precision to distinguish between solid rocky and water-rich planets and between giants. But now it is clear that we need at least 2% precision in the planetary radii for further characterization of the interior structure and planetary evolution and so on. And you can see that the present precision is not like that. And PLATO will do the job, part of the job, because it will have better photometric accuracy 10 years from now. And this will decrease the error bars, but this is not enough. There is another part which is needed to decrease these error bars, and I will speak about these things. And it is not enough just to decrease the error bars, because here in this planet mass, planet radius diagram, you can see that if we add some gas or water to the solid parts of the planet, then the mass radius diagram will become immediately degenerated. It is quite hard to distinguish just from planet mass and radius that what is the interior structure of the planet. And another problem that if we have transmission spectroscopy and we want to study the planetary atmospheres, then these theoretical models shows very small differences in the planet stellar radius ratio, which is on the x-axis, how it varies as a function of the wavelengths. And the difference is in the order of 0.1%. So the determined planetary radii should be as precise as 0.1% at least, or even better, because sometimes we are searching for even smaller differences in how the planetary radius changes as a function of the wavelengths. So the radius of a transiting exoplanet is determined from this very basic equation, where we have the flux drop due to the transit, delta F, normalized to the out of transit flux F, will be a function of the area ratio of the planetary and the stellar radii. There are at least 3 problems with this equation. The first problem is that how precisely we know the stellar radius, because we cannot know better the planetary radius as we know the stellar radius. And this is a problematic little bit in these days. The second problem is how precisely can we measure the normalized flux drop, because this is affected by out-of-eclipse variability and not only by just the photometric precision. And the third problem that this equation is not true at all, because at least we have the limb darkening, which is a function of the limb darkening coefficients, which are functions of temperature, wavelengths, log G of the star, metallicity, and so on, and on the projected sky position. and we have contaminating sources. For example, this is CoRoT1 on the POS images, and this zigzag line shows the photometric mask of CoRoT. This is a real CoRoT image, but these small contaminations or big contaminations are routinely taken into account. So yesterday we could see, for example, in Eike's talk or in some other references in the last years, that there are many faint companions within 1 arcseconds to the stars, but many of them seems to be faint enough that we can neglect them, and the other remarkable, more distant optical or real companions are routinely taken into account. So this factor here, the contaminating flux, is relatively well known. But of course it causes some uncertainties. But the limb darkening is a real problem in this left figure. This solid line represents the non-limb darkened transit light curve from the center of the transit to the end of the transit. This is a theoretical calculation of Mandel et al. From 12 years ago. And these different solid, not solid, but dashed and point dashed curves represent different limb darkened light curves. And you can see that the transit depth can change by a factor of 2, so that it is not a negligible effect. A real measurement can be seen on the right hand side, on the right figure, from the bottom figure is at 0.3 micrometer, the top figure, the red points are around 1 micrometer. And believe me, the lengths of these two lines here and here are the same. And you can see that the transit depth changes very much against the wavelengths. So we have a much deeper transit in blue than in red. So let's characterize these factors one by one. Let's start with the stellar radius. So today, the source of the stellar radius comes from isochron fitting or empirical scaling relation, or for very bright stars we can do interferometry, but this has other uncertainty. For example, the distance is not very well known. So if we start from the Kepler's third law, and we neglect the mass of the planet, and we divide by the stellar radius, we have this very simple equation where the period can be measured easily, and the scaled symmetry axis is related to the duration of the transit. Then we have one parameter, that's called density parameter on the y-axis. We have the effective temperature measured from the color or the spectrum of the star, and we have many theoretical isochrons. These are just schematically shown here. And with some error bars, we can locate the position of the star here. Yeah, the duration of the transit can be measured easily, the period can be measured easily, but the effective temperature will have at least 100, 200 Kelvin errors, which should be propagated into the stellar radius. And there is another problem. Stars have spots. This is, for example, a model of the binary star SV Camelopardalis by Jeffers, and they found that it is a heavily spotted star. Or CoRoT2 was measured by Lanza et al., and they have spots practically everywhere on the stellar surface. And a recent study, Jackson and Jeffrey stated that there can be many small spots, hundreds of spots on the star, which will cause spectroscopic activity indications. So, for example, the calcium H and K lines can be seen in the spectra, but there is no photometric activity, because when a small spot disappears on one edge of the star, and the other one will come from the other edge, and practically the spotted area does not change. If this is true, then we have serious problems, because there are older and fresh studies by Spruit and Weiss, Jackson and Jeffries, that the spots change, the measured stellar radii, the effective temperature, and the internal structure. Toulouse et al. Called the attention in 2009 that stars with mass below 1 solar mass have systematically different radius from the theoretically calculated ones, because spots falsify the temperature. What we measure is an average, a weighted average of the spotted and the unspotted area, but the total luminosity of the star does not change. So if the temperature is falsified by spots, then the radius should be falsified as well. And last year, Guillermo Torres had a nice overview about the basic properties of late-type stars, and due to spots, magnetic inflation, or due to the problems in the convection theory, there are 10–50% systematics in the low stellar mass radius. There's a nice figure taken from Torres' paper, Here you can see the mass of the stars, the radius of the stars. These are very good measurements, mostly based on two-line spectroscopic binaries. These are the black points. And this gray area are the isochrons from 1 gigayear to 13 gigayear. And you know that the stars are evolving from these isochrons to up when they leave the zero-age mean sequence. So there are many stars which are not in the gray area, which means that they should be older than the universe, which is strange. Or they should come from another universe, from a parallel universe, to have older age than our universe. Or we have a problem, and this problem is related to the spots. So if you look at, for example, this example, this has 50% bigger, almost 50% bigger radius what was predicted by the unspotted stellar models. So hopefully there will be some progress in this field, and we will have better stellar radius. Because otherwise this is propagated to the planetary radii, and we have a problem. So today, only the double-lined spectroscopic binaries can provide reliable stellar radius. But in the near future, the ongoing Gaia project will provide distances to the stars with a very good astrometric accuracy. So the luminosities will be known very well. But the temperatures cannot be measured cannot be measured better than today. So if we calculate the radius from the famous luminosity radius temperature equation, this cannot be better than 4 to 8% because the temperature determination will depend on the log G, and the spectral theories and the stellar atmosphere theories won't be improved so fast in the near future. And the next talk will be discussed this, hopefully. So in the far future, we have the chance that PLATO will give the astroseismological constraint for the density parameter, the mass and the radius. And this also depends on the temperature determination of the star. So this is one of the key parameters and I have no hope that the temperature determination will be improved significantly in the future. But if we combine PLATO and Gaia data, then it is possible to reach the 2% accuracy in the stellar radii according to the yellow book of PLATO. And yesterday we had a talk about what is the present situation in stellar masses and radius if we base it on astroseismological results. So the second problem is the contamination factor. If we have a background star or galaxy, then there is no problem. Then we can routinely remove it from the measured transit depth. But if we have a spot or a bright facula, then the transit depth will be different. And this is a time-dependent phenomenon. In my categorization, there are at least 3 types of spots. So one is which is not occulted, and this can be removed by baseline fitting or selecting the deepest transit points. This is done routinely. The second type of the spot, when the planet crosses the spot, then this also can be removed by detailed spot modeling, which has some details, which is not discussed here. But with careful analysis, it can be done, and it was done. CoRoT2 is a very good example, so it can be removed from the observed transit. But type 3 spots can have long lifetime. They can be close to the pole, and if the star is not rotating or it has slow rotation or the rotational axis is such that it is perpendicular to our line of sight, then this spot won't cause any modulation in the light curve. Or even the spot, we can look the stellar pole somewhere here, so this kind of spot also not cause any kind of photometric modulation. So it is hard to remove from the light curve because we don't know what to remove because we don't have any spot signal. So in this case, the temperature will change as we discussed before, but the limb darkening coefficients will be changed as well because limb darkening coefficients has a temperature difference, so the limb darkening will be different in the spotted area and in the unspotted area. And if we have many other spots, then the situation is even more complicated. We have to calculate some nice weighted average. And of course, the spots will cause extra positive or negative contamination depending that they are bright or dark. So the conclusion that the primary effect of stellar spots on the transit depth And on the contamination is that the transit depth will be smaller or bigger, depending that we have bright faculae or dark spots. The baseline change, which can be fit or corrected. And we have an extra positive or negative time-dependent contamination. And it is also problematic that if we fold a light curves, then how to average them and how to fold them and bin them at all, because due to the time dependence of stellar activity, we fold something which is not stable enough. So the folding should be done very carefully. The next satellites will be monochromatic too, like CoRoT and Kepler, so multicolor photometry won't help too much, because there is no multicolor photometry in this thing. So the last part of this equation is the effect of limb darkening on radius on transiting exoplanets, which can be a factor of 2 modification. So this picture shows the sun, our sun, and sun is the only star where we can see directly the effect of limb darkening. And actually this picture was obtained during a Venus transit, so this is Venus. This is practically the size of Earth, so if we search for exo-Earth, we have to search a point or a circle or a disk like that. So if our object, which is a hot Jupiter, which is much bigger, is close to the limb, we have smaller amount of light coming from here, and if the Jupiter-sized planet is close to the center, then it blocks more emission because the stellar disk is much brighter. This happens in dwarfs. In giants, we have the opposite. It can have limb brightening. So if we knew the limb darkening coefficients and the laws of limb darkening, how the intensity changes from the stellar center to the edge of the stellar disk, then we could reduce the number of free parameters, which is always very good when we have degeneracies and many free parameters in a fitting. But first of all, I would like to call your attention that the stellar parameters are not absolutely precisely known. So in the effective temperature, a typical error bar today is 100 Kelvin. In log G, it is 0.1 in the best cases. In metallicity, it is also 0.1 in the best cases. So when we take a limb darkening table, which predicts the values of the limb darkening coefficients for a certain effective temperature in log G and metallicity and turbulent velocity, then we have to propagate the errors of the stellar parameters into the prediction of the limb darkening coefficients. In most of the cases, this is not done. There is just a simple interpolation of the limb darkening tables, and during the fitting procedure, these limb darkening coefficients are fixed quite often in a paper. But this is bad because we cannot know better the limb darkening coefficients than the values coming from the stellar parameters. And the second problem, that to measure the planet-to-stellar radius ratio, let's say with 5% uncertainty, we really have to know the limb darkening coefficients with a precision which is about 0.5%. But if we propagate the stellar parameter errors into the prediction of the limb darkening coefficients, we already have 5% error in the limb darkening coefficients. So this is bad. It's a bad idea to fix the limb darkening coefficients. The second problem, that if we compare different theoretical calculations to each other, for example, in this figure, 5 different calculations of one-dimensional stellar atmosphere models are compared. On the x-axis, here we can see the temperature. On the y-axis, we can see the limb darkening coefficients. The solid curves are the linear one. The dashed curves are the quadratic coefficients. We can see that sometimes around this temperature range there are relatively good agreement. In some other temperature ranges, we have bad agreement. So on the right figure, I propagated these theoretical uncertainties into the relative error of the stellar to planet radius ratio, and in most of the temperature ranges, it is over of the 2% level, over the 2% level what we want. For these two curves are for 2 different impact parameters. And I had a nice story. I modeled CoRoT13b for a CoRoT paper, and I found that it should have a position close to here. This red square shows the position on the mass radius diagram. And you can see that it has a very high density. And there is no any other planet in the vicinity of this CoRoT13b. So later, 1 year later, another study by other authors was published, and they found that their best solution has bigger radius, so smaller density, and it is much closer to the clump of the other planets. But they did not accept this best chi-square solution in the other study because the limb darkening coefficients were unphysical, but they found that the star has limb brightening instead of limb darkening, which is quite uncommon among the dwarf stars. So they constrained the limb darkening according to these theoretical tables, and finally they choose this blue point, this position, which is absolutely very close to the clump of, or for the majority of the other planets. Okay. 2 or 3 years later, a three-dimensional stellar atmosphere model appeared by Nielsen and Lester, and they also changed the stellar geometry from plane parallel to spherical. You know that stars are plane, like the plane Earth and so on. These old things, not spherical. But however, what they found, that the old limb darkening coefficients with plane parallel geometry were the red points somewhere here. And with the new ones, they are around 1, and if it is limb darkening coefficient is 1, then we have limb brightening. So later theoretical calculations proved that we can have very interesting limb darkening coefficients if the star is not a plane, but it is a spherical object. And then CoRoT13b should be stay here. And meantime, new objects were found, WASP-64b or a Kepler KASC-7 objects, which has practically almost the same properties. So it is a good story of science, I would say, that you have a limb darkening coefficient, which was checked, observationally checked only on the Sun, and it was not checked on any other star, because it is impossible to do it at the moment. Only eclipsing binary stars can be used for this purpose, but they were not used very frequently. Only a dozen of examples can be found when they checked the limb darkening coefficients. And actually, what they found was a disagreement. So you fix your limb darkening coefficients, and you base your fit onto a not checked and not tested theoretical calculation. So this is bad. And even more calculations appeared in the literature. So last year we found new calculations. This is an interesting coordinate system on the x-axis. So 1 means the stellar center and 0 means the limb of the star. And the old calculations shows this kind of behavior, how the stellar intensity decreases from the stellar center to the limb. And the new calculations are on the right figure. It is a solid curve shows it. And all the dashed and point dashed curves are different limb darkening laws, which are approximations for the real intensity distribution. And what I would like to show that, look at the edge of the star, the limb of the star, when the intensity suddenly drops to 0, which means that the very edge of the star, about 2-3% of the stellar radius from the edge, does not radiate any emission into our direction, and we cannot see it. So the star is bigger in reality than what we can see. If this theoretical stellar atmosphere calculation is good, because this is also not checked yet, it is also not tested observationally. But it means something like that the real star is this whole circle, and the shaded area around the limb, it is not visible from Earth. So if we take Kepler's third law and the real stellar radius, then the observable transit should be like that, which is much wider than what we observe in reality, because the very limb of the star is not visible from Earth if this calculation is correct by Nielsen and Lester. So we observe shorter transit duration. Fortunately, the effect is not big, but it can affect the scaled major axis systematically. And of course, if we have spots, then the temperature of the stellar photosphere is different from the unspotted temperature. So what we have to measure observationally is a weighted average of the spotted and unspotted areas, and the limb darkening coefficients can be different from the theoretical tables, because when they are calculated, the spot effect is not taken into account, and they can change the limb darkening coefficients by a factor of 2, which means that this does not help to us when we want to test the theoretical calculations. So my summary: stellar spots have impact on transit depth, which can be maybe managed, and on the temperature and radius determination of the star, which has some progress, but it is not finished yet. They modified the observable limb darkening coefficients. Maybe this is understood, which was published last year. And we need 3D models, improvements in convection theory, spherical models instead of plane parallel models, including stellar activity and good observational test of these theoretical calculations. And maybe in the future we will have much better photometry and much better stellar parameters. Thank you very much.
Thank you, Szilard, for this nice talk and the insights you gave into the half-life of a transit model. So we have time for a few questions.
You showed those limb darkening calculations. And actually, the stellar properties are 10 solar mass and log G, so that's a supergiant. Is this effect the same for main sequence stars? Do you remember it?
Yes, the dwarf stars has the same pattern, so the intensity drops to 0 at the edge of the star. I know that this figure is not the best one, but when I collected the papers, so Nilsson published first the paper for the giants and then the dwarfs, but the dwarfs have the same behavior.
Of course, measuring the limb darkening with interferometry for solar-like stars will be difficult, but for giant stars it should be possible. Has there any study been done between theoretical limb darkening curve and interferometric limb darkening for giant stars?
Yes, yes, started, I think, yes. There are programs ongoing, that, as far as I know. But, yeah. And then, of course...
Thank you. And on the stellar radius, I think we should note that we have done rather better using astroseismology already than what you indicated. In the case of Kepler, we have astroseismic stellar radii for about 100 stars based on global astroseismic parameters, and for quite a few stars based on individual frequencies. And so for PLATO, we certainly hope to do much better, of course. And not just to get M over R cubed, but to get detailed information about the stars, including the radii, masses, and radius. So the future is not quite as black as you might have painted in your talk.
Thank for the comment.
Yes, but you're right. But in the same time, you are still stick to the effective temperature determination and metal content. Yeah. It's okay.
Hi.
Hi.
Comment on the question.
Yes.
So with CoRoT3, I had a look at this, and I found that the two different CoRoT light curves, the short canes and long canes, didn't agree with each other at all for the same star. And so where you think the radius of the planet is depends on which set of data you happen to believe. And I think that is the main problem with CoRoT3. And then the question is, with this, back with the limb darkening, and you've shown, as have several other people, that it goes down to 0 before the limb of the star. So firstly, do we redefine how big a star is? Secondly, could we test this on the sun?
I'm not sure that I understand you very well, but my basic point that I don't believe any limb darkening tables which is on the market at the moment. They should be bad because they have one-dimensional model or plane parallel models. The 3D models and the spherical models can be much better, but they are observationally not tested yet, and this is why I am not believing it. When they are observationally tested, I will accept them if the observation shows that they are good. And if I take this into account, then I would say that it is much better to leave the limb darkening coefficients as a free parameters than to feed them and accept them whatever they will show. And we can calculate not only the chi-square values, but the information content based on some definition of the information content. And if they show that this is a better fit of the observed data, then I would choose that one instead of a physical constrained model, because I don't know that these physical constraints are really physical reality or just physical constraints of the input model.
So maybe time for our last question at the back of the room. Otherwise, we're going to be late for the coffee break.
Well, I'm happy to announce that there are limb darkening tables now for the grid of 3D simulations you cited up there in one of your slides. And of course, it has been tested against the sun and looks pretty good there. And I'm going to test against whatever transit-like curves that can give constraints on limb darkening. One other thing, the limb darkening of my simulations is ill-matched by just a linear or quadratic, and you really need to go to a Claira's 4-parameter limb darkening fit, and that works beautifully for all cases. But I then propose to, if you need to fit to observations, that you then keep one of the parameters free to match your observations if that's needed.
Yeah, if I look at this solid curve, how complicated it is at close to the edge, then I absolutely agree with you that a 2-parameter law is not enough.
Well, that issue that's a different one, and that must be because of this is a giant and it has a large difference in radius, in effect in photospheric radius depending on wavelength.
So thank you again, Szilard.